So today we're going to look at some definitions of key terms for the graphs of polynomials. There are quite a few, so I would make sure that you're pausing and writing things down as I go. I'm just going to try to get through all the definitions before I then look at some organizational tips for you, as well as some additional things that can happen with graphs. So the first definition is an increasing interval, and basically what it says is as x increases, f of x increases. Algebraically speaking, it means that if the first value is less than the second value, then the output created by that first value will always be less than the output will be less than the output value by the second value. So let's take a look at what that's saying. A lot of students, they read that and they have a little trouble understanding what it's saying. But here's a clearly increasing function, right? So this is clearly going up the whole time. So what it's saying is if I have an x1 here and an x2 here, that x1 is always less than x2, simply meaning that the x values are going upward. So what does f of x1 mean? It means the corresponding output value, f of x1, will always be less than the corresponding output value f of x2, because f of x2 would have to be larger in order for it to increase. So it's saying, basically it's saying as x goes up, y goes up, okay? So how do you find it? You simply examine the graph and determine the domain, it's answered as a domain, of the intervals where the graph tends upward. Now, the other idea here is something called a decreasing interval, which is exactly what you expect. It says as x increases, then the output values will decrease. And so, a visualization of that, same idea, but going downward. If I have a function that's clearly decreasing, like this function, and it's tending downward, then x1 will always be less than x2 because you read the domain of a graph from left to right. But in this case, f of x1 is actually larger than f of x2 because f of x2 is smaller because the graph is going downward, meaning the trend of the graph. And the way you find it mathematically is you simply state the domain in which this is happening. Okay, and the next thing that's really important is relative and local minimums and maximums. So a relative or local, these are synonyms. A relative or local minimum is simply a point where the graph changes from an decreasing to an increasing interval. So let's say a graph is going downward and then all of a sudden it goes upward. This is where a local or relative minimum is right there. How do you find it? You simply look at the point where the graph changes from increasing to decreasing. You can see clearly here the graph is decreasing here, but then increasing here. All right, the absolute or global minimum would be the smallest of these that you see. So let's say you had several of them, right? Let's say you had a graph, okay, like this. Then this would be the global minimum. But keep in mind that if the graph actually stops here, this is also a minimum, and that would be the global. The smallest output value on the graph is the global minimum value. So for relative maximums, it's the exact reverse. It's where a function changes from an increasing interval to a decreasing interval. So you can clearly see here that the graph is tending upwards and then stops and then starts tending downward here, giving you the maximum here. And a global maximum is the exact same thing, but in reverse concept as the minimum. So if a graph that does this, this one would be the global, but if it then goes up like this, this could be the global maximum too. Endpoints can be globals and they can be locals. So keep in mind that this would be a local and a global. This is the obvious local minimum, obvious local maximum. This would be a local and a global as well. An X-intercept is simply a place where the graph touches the x-axis. Many can exist in a function. You can have many of them. It is written as a point, whatever that value is, comma 0. And the way you find it is to substitute y equals 0 to a function and solve. You've done this many times. Like the last time you saw this, if you have a quadratic and you have something like this, right? The way you would find the x-intercepts of this quadratic is you would set the problem equal to 0 and solve. In this chapter, by the way, a quadratic is a type of polynomial, but in this unit, we're going to go to higher exponents than the square. The y-intercept is a point where the graph crosses or touches the y-axis in a function that only one can exist, you do this by plugging 0 in. So a lot of times it's called f of 0. Using this example here, you would have 0 squared minus 0 minus 12. So that one would be 0, 12. Again, every function has a y-intercept, but not every function has an x-intercept, or they could have more than one. So you could have one, none, or many. You do this by substituting y equals 0 in, or f of x equals 0. This one you complete and figure out by plugging 0 in for x. So to go to a couple more, here's a new one called an even function. Even means a function is even when it's symmetric to the y-axis, meaning it has a line of symmetry of x equals 0. So algebraically, you find that by plugging a negative in, and basically the negative will be canceled out by all the evenness of the graph, and you get f of x back out. An example of that, a very obvious even function, is the quadratic. So let's say I have f of x is equal to x squared minus 2x plus 3. That is not going to be even, though, because it will only cancel out here. So let me show you what I mean. If I put in negative x squared, so the exponent does not mean it's even. You have to actually look at this happening and see if the function will basically return the original function by plugging in a negative x value. So f of negative x is going to come out to x squared positive now, because a negative times a negative is a positive, minus 2x plus 3. But that negative there, because we have to plug a negative x into both, would make that a positive. So these don't match. So that's actually a neither. In order for this to be even, we would have to have a quadratic like this that doesn't have a middle term, because that middle term is going to cause issues with that elimination of that term. So if you remember what happens when we eliminate the middle term, and I'll show you a picture of this. So as you can see here, by eliminating the middle term, when I put a negative x in, I got the same function back. That's what you want. So graphically, the difference there, and this is important to understand, is that the first problem was some kind of parabola over here or over there. But this one, if you remember, the vertex of this parabola was 0, 3. So if you look at where this graph would be, it would just be up here 0, 3, and it would be perfectly symmetric to the y-axis. Another example of this, which we have seen, is if we had an absolute value graph on the y-axis. Notice the symmetry to the line y equals x has a line of symmetry at x equals 0. For oddness, oddness is very similar to this, but what happens here, it's a little bit more involved. So if I put a negative x into something that's odd, remember the entire thing would have to obey this rule. So if I put negative x into, obviously it wouldn't work with an even exponent. Again, it's not the exponent, it's the algebra, and for us, really, it's about the graph. So over here, if I had something like this, x cubed plus x minus 3, what's going to happen? I'll make it plus 3. I'll make it a little bit more obvious. If I put a negative in here, it's interesting what happens is I put the negative into this graph. In the first two will, in fact, become negative f of x, meaning opposite of the original. But the problem I have is that 3 isn't going to change over. So it doesn't change, right? So I have this happening where I get negative x cubed, and that's what this is saying. You need to be able to have a negative in front of your terms. This will change. Sorry, I wrote that down wrong. That's an addition. So it'll become minus, so you have that negative x. But the problem is the 3 doesn't. So in order for this to be odd, you would have to lose that 3, and now you can see that every term changed signs. And so what does that look like in a graph? And this is what really matters. If you're really concerned, like, well, there's a lot of algebra going on there, what really matters is you have a symmetric to the origin, right? So in this graph, if I had a graph that went like this and then had a perfectly symmetrical to that, that's an example of oddness. Symmetric at the origin, the point 0, 0. It's point symmetry as opposed to this, which is line symmetry, okay? So just keep that in mind. Even for, is symmetry to the y-axis, odd is symmetry to the point 0, 0. Though many graphs are symmetric, only graphs that are symmetric and meet these characteristics are called even or odd. So you can have symmetric graphs, right? So you could have a graph that's perfectly symmetric, a perfect circle. But is this graph symmetric to the y-axis or the origin? No, it's symmetric to this point over here, which is irrelevant. They have to be symmetric to either the origin, odd, or the line x equals 0, the y-axis. There's something else called end behavior, which has a lot to do with domain and range, and you see it quite often like this on an assessment. And I put up here a translation of it. So end behavior is the comparison of the domain of a function with corresponding range elements. And so what that's saying is that x is going to go to the left side of the domain, and then you're going to tell me which part of the range that it's corresponding to. And then we're going to talk about x going to the right side of the domain, and then talk about its corresponding range elements. So let's take a look at a couple examples. The best way to understand end behavior is to see it, because you've already done it with domain and range, and it's just a new way of writing it. So if you ever see a computer-generated graph like this, please ask your teacher if there are arrows here. It's actually hard to get a computer to do that many times, so just keep that in mind. All right, so if we look at the domain of this from before, it would start at the left, beep, the whole time. So we have the domain goes from negative infinity to infinity, little review, and the range starts at the bottom here, right? So as we talked about before, we're going to label these axes because we see infinities in a lot of places. So if we start at the bottom, we would start right here and beep at -4, beep to infinity. So that would be 4 to infinity. So a little review from before, but now what's going to happen is we're going to splice this up basically. And what happens is this infinity is the left side of the domain. And so the question is, which of these range elements corresponds to the left side of the domain? And you don't have to use both of them. You might use one of them twice or one of them no times. So on the left side of the domain over here, the range is going to infinity. So you say on the left side, negative infinity, the range is going to infinity. And on the right side, which is this piece, right? So this piece right here is going to infinity, the right side of the domain. So over on the right side of the domain, what is the range doing? It's also going to infinity. And then students will immediately ask me, well, what about the 4? The 4 is the middle behavior. Notice the name, end behavior. Yes, 4 is important in the range, but it doesn't tell you what's happening at the ends of the graph, the extremes. I've actually seen this called extreme behavior, but in Virginia we call it end behavior. Let's take a look at one more in which we will be using the range a little bit. So I just gave you guys a line here. And if you notice, again, don't have arrows. So we're going to put arrows on the graph. It helps to label my axes. So here we go. All right. And so what I'm going to put in here is the domain beep the whole time, negative infinity to infinity. The range is just one number. It's just, watch, beep, beep. It's just 3. So if we take a look at this example, on the left side, the graph is going to negative infinity, but what is it doing? It's going to 3. And on the right side, the graph is going to infinity, but what is the range doing? It's also going to 3. So try not to get bogged down about using the range every time. Try not to get bogged down about using each piece of the range. It's saying, look only here. I don't care about the middle. Just look at the arrows and tell me what the arrows are doing in terms of the domain and range. This is one of those times when there's a lot of vocabulary, but the actual work isn't so bad. So we're just going to go over a couple more terms. One of them is just a kind of overview of the different types of polynomial graphs and the significance of their terms, their coefficients, lead sign, what the graph looks like, and what end behavior does. So what I would do, again, I would pause the video. I'd make a chart that has 5 columns, and then 1, 2, 3, 4, 5, 6 rows, actually 7 because you need the title. So go ahead and make that, and then we'll go over it together. All right, so the first thing we need to know is what is a linear polynomial. We've talked about it before, you've seen examples, so this is just kind of putting things together. A linear polynomial is something that has a variable with only one an exponent of 1. So something like this, right? 3/4 x plus 2 from algebra 1 is a linear function, but it's a linear polynomial. A quadratic would have, as you've seen many times, it can be, you can have all kinds of numbers of terms, but you're used to seeing quadratics with 3 terms, otherwise known as a binomial, a trinomial, and that function is pretty classic at this point. Cubic functions can have a whole string of things, but a cubic function just has to have a lead coefficient that is a 3, right? It could just be a cubic binomial. A quartic has a 4 on it, as you well know. It can have other things in there too, right? So your quartic function could have a 4 here and then have other terms in the middle, for instance. Like you could have a square and then you could have a constant. And then so on. A quintic is going to have a 5 as an exponent. And then we went up to 6th degree, because at that point, it does get a little bit redundant, and you're going to start seeing patterns at that point. So what is the first pattern we see? Well, why don't we start with a typical graph of the first couple, and I think it'll be delineated a little bit easier for us. So if we take a look at a typical graph of a line that has a positive slope, it just looks like this. That one went through the origin. Maybe I'll put one up here that has a y-intercept of about 2. In a quadratic, right, it looks like a U. So a quadratic would look, like this. And then a cubic, as we learned back in Unit 2, has 2 terms in it. Kind of looks like an S. I'm going to accentuate them because we're in the polynomial chapter. So a cubic would look like this. So these are all positive lead coefficient examples. You can understand that from the world of slope. It goes up. Quadratic is pointing upwards, and this cubic, is going in the positive direction from back when we learned it in the Transformations chapter. So notice, first thing, before we start talking about negative coefficients, I'm just going over right now, I'm just going over like a review of what this chart does and what we already know at this point. So if you look at a line, what is the maximum number of turns a line has? 0. There are no turns in the graph. However, a quadratic has 1 turn. And a cubic has 2 turns. So you might already see the relationship that's forming. The exponent is always 1 more than the number of turns. Another way of saying it is the number of turns is always 1 less than the exponent's degree. So now let's talk about negative lead coefficient signs. So these are all, again, just review, and then we'll take a look at the other ones once we understand this pattern. So here, right, for these, what we end up getting is we end up, for a line, we get a graph that tends downward, right? It has a negative slope. For a parabola, we're going to have a parabola that opens downward. For a cubic graph, believe it or not, it looks exactly the same, but this part will go down, this part will go up, so it ends up looking like this. Okay, and you might remember that from, that would be if it had a reflection over the x-axis. So the turns aren't affected by the sign of lead coefficient, but the end behavior is, which why don't we go ahead and take a look at that right now. So for a typical line, the domain is negative infinity to infinity, so I'll just start by writing those in. Okay, negative infinity to infinity is a domain, and the range goes, right, on the left side, it's pointing downward, so the left end behavior will provide a negative relationship, where the right end behavior will provide a positive relationship. And for a line going downwards, the only thing that changes is we still have, right, we still have a domain, beep, of negative infinity to infinity. However, the end behavior switches, right? It's going to go up over here, right? It's pointing upwards. So it's going to go infinity on the left side, and on the right side, it'll go to negative infinity. All right, so for a parabola, we have the situation where This side it's still going negative infinity to infinity in the domain, right? I mean, that makes pretty good sense, right? Because we're saying beep the whole way. And the end behavior here is they're both positive. They're both pointing up. On the left side it's pointing up, and on the right side it's still pointing up. Okay, and so then we go to the cube graph, and you'll notice hopefully which one has been repeated. Oh, I'm sorry, so we've got to do the negative quadratic graph. So the negative quadratic graph still has the same domain, right? However, the outputs, the range values, they're now going to negative infinity. All right, so now we're going to look at this one. So this one, as x goes to negative infinity, the domain is still beeps the whole time, so it's still negative infinity to infinity. Notice this is just the domain going downward. Here, it's going to negative infinity, the range is, right? It's going to negative infinity. And here the range is also going now up. So as you can see, let me do the next one, it's repeating one that we've already seen. And this is the point of this whole chart, is to show you these repetitive things that happen with polynomials. So for this one, domain's negative infinity to infinity, it's pointing up, so f is going to infinity in the range, but on the right side where x is going to infinity, the range is going to negative infinity. And you can see the correlation between this and this. And these are both, right? This is a linear, and this is a cubic, and I bet you might be able to figure out the next one of these that'll repeat is we'll have another repetitive one here, right? These are all going to follow the same end behaviors. So what do we fill in these charts? You can see the pattern. If this is linear, we have no terms. Quadratic has 1, cubic has 2, so quartic will have 3. And if quintic will have 4 turns in its graph. And a 6th-degree polynomial will have 5 turns in its graph. This pattern here is obviously just talking about positive and negative, so that's just to determine what the graph's going to look like. And then here for the graphs, that's when we want to do a little practice of the actual drawing of the graph. So if I draw a graph with 3 turns in it, right, it's going to look like this. 1, 2, 3, and you can see that it's going up. When I draw one similar to that it has a negative, it flips over, right? So it's going to look like this, 1, 2, 3, still 3 turns, but now it has the end behavior that is similar to, big surprise, the quadratic. So even degrees will have similar, will have the same end behavior for polynomials, and odd degrees as well. So let's just see if that holds true for the rest of it. Okay, so here we would have 4 turns. Okay, so we're going to start, okay, so we're going to start like this. So 1, 2, 3, 4 turns. There we go. And if it goes downward, it'll look like this. 1, 2, 3, 4 turns. There we go. 1, 2, 3, 4. And for a 6th-degree polynomial with 5 turns, 1, 2, 3, 4, 5, it goes back up. And then 1, 2, 3, 4, 5, it goes back down. So I went ahead and filled in the rest of this table, and you can see the pattern here. When you have an odd degree, this being 1, this being 3, this being 5, you have the pattern that the end behaviors of these graphs will always be identical, and the identicalness is that they alternate, as opposed to an even degree polynomial, which have the same end behaviors, but instead of alternating, they match. Positive, positive, negative, negative, positive, positive, negative, negative. The way to remember this is to understand that the right side end behavior always matches the sign of the lead coefficient. So as you can see here, do you see how this arrow matches the positive? So does this arrow matching the positive. This arrow matches the positive. This arrow matches the positive. Same thing with the negatives, right? So if I look at the negative ones, negative matches negative. Doesn't matter if it's even or odd. So what you really need to remember, it's really just boiling down, and this is a huge chart, but it boils down to this, okay? whatever the right side is matches the lead coefficient sign. And if it's odd, it will alternate from there. So you start at the right and then you go to the left. So if it is odd degree and it's negative, it'll be negative. Odd means the other side's the opposite. But if it's negative and it's an even degree, it'll still be, right, it'll still be negative. The right side will go down, but even means the same direction as opposed to odd, which means opposite direction. Maybe just think about it like that. So a lot of work. You don't have to memorize this chart. That would be obscene, but you might want to understand these relationships. The number of terms in a polynomial is always one less than the degree. That's pretty easy. You can see that here. Quadratic is 1, cubic is 2, quartic is 3, number of terms. The sign of the lead coefficient always matches the right side in behavior only. That's what I was just talking about. Once the right side in behavior is determined, the left side in behavior matches the polynomial when it's even and is opposite if the polynomial is odd degree. And please keep in mind that even and odd here is not talking about symmetry. It's talking about just the lead. It's just talking about the degree, not the symmetry of the graph. So the reason this matters is something like this. Okay, so imagine you get a problem like this on a standardized test. Which of the following polynomials could have a maximum number of 3 terms? If you understand these 3 sentences, this one is simple. It's D, right? All you have to do is look for a lead coefficient that has a degree of 4, because it has 3 terms. 3 terms is a quartic, even if they put all these A, B's, and whatever. So look at this example. Which of the following polynomials could have an end behavior in which the left side goes up and the right side goes down? Well, there could be more than one of these, right? Because if you think about this, again, what matters is the fact that they don't match, and they don't match in problems that are odd degree. And that's the reason we learned it. Again, do you have to memorize this chart? No, that would be obscene. You need to understand what these 3 sentences are saying and be able to apply it to a standardized test. So there is a little bit more that we need to learn about polynomials before we start some examples. And I know that there's a lot here of information. You have to trust me that the information is not very difficult to actually compute when you look at a graph. In fact, there is no computation. It's just basically identification. So the actual problems are quick, but there's a lot to learn in terms of vocabulary. So this is the last little bit. Within polynomials, you can have something called multiplicity, which means that you have a root that occurs more than once. And we have actually seen this with quadratics. So let me just give you a quick little window into it the last time we saw it. So in the world of quadratics, you can have a graph like this, and it has 2 roots, and everything's good. But if you remember, we could also have a quadratic that would land on the axis and have its vertex on the axis. So the root of this conversation that we're having actually goes all the way back to Unit 2 for transformations. And what this is saying is that this right here, and you might remember it, let's say this is at -2 on the x-axis, the function would be f of x or y equals x plus 2 squared. And what that really means, remember, squaring something means to write it down twice. So it actually would be x plus 2 and then another x plus 2. And that would produce what's known as a double root, meaning it has 2 factors that have the same answer. So a double root, algebraically, is a factor that occurs twice, just like it did back here where we had a quadratic at -2 producing a factor of x plus 2 twice. Graphically, it's an x-intercept that appears quadratic even in a polynomial that could have a larger degree. And that double factor will produce one x-intercept, and we call it a double root or a double zero. So here's an example of a cubic function. Here we have what's known as a linear root, meaning it crosses the x-axis 1 time. And here we have a double root. It looks just like this, but it's contained within the shape of a cubic function. So another way to explain this that I like to mention to students is if I were to cover this part of the graph up, okay, so let me cover that up. So if I covered this up, this looks like a line. That's why it's called a linear root. But if I cover that up, it looks like a quadratic. So it has to do with the shape. This looks like a quadratic as it hits the x-axis, making it a double root. This looks like a linear graph crossing the x-axis, making it a linear root. So over here we have a graph that's a quartic, straight from this table that we just learned about, right? It's just like a graph like this one, but I moved it to the x-axis. And it actually has two double roots. So it has one here. Look, that looks quadratic. That looks quadratic right there. And so that graph would have two double roots. And this is the result of those double roots. What would happen is this function basically could be kind of discerned right now, because we could call this function f of x. We know that this function has three, right? It has three factors because it has a cube in it. The first one looks like it's about negative, let's just call it -3. It's a little bit past it, but we'll just say that this is at x equals -3. So if this is at x equals -3, then the factor would be x plus 3, as we learned back with quadratics. This one is going to be x, that one's clearly at 3. So that would be, if this is at x equals 3, what happens is this actually occurs twice, x minus 3, x minus 3, but we don't leave it like that. We would simply write it as x minus 3 squared. Okay, over here, if this was a function called f of x, then this would have a factor at x equals -2 and x equals 2. They would both be, right, double roots. So when I wrote this one down, it would be x plus 2. And when I wrote this one down, it would be x minus 2. And they both would be squared. And these, if you add them all up, remember this is 2 here, and this is 2 here, that comes out to 4. And if you add all three of these up, because this one is 2 of them, plus that one, that would be cubed. So the big idea here is, when you look at this, when you look at this graph, linear root has a 1 on it, quadratic looking graph is a double root, has a square on it. This one has a quadratic looking graph and a quadratic looking graph, making both of them squared. And in fact, this concept can actually go beyond this, just to have looking like a quadratic. It can also look like a cubic function, and that would be called a triple root. So a triple root, same idea. It's a factor that occurs, and I thought I was being funny here because I said a factor that occurs twice, a factor that occurs thrice. That is a real word. It means it happens 3 times. And it would simply be x plus or minus a number cubed, as opposed to x plus or minus a number squared. And the x-intercept would appear cubic in this world, and it would be a triple factor that would only produce one x-intercept, called a triple root or a triple zero. So here we have a linear root, and here we have a triple root. Let's just take a closer look at it. Again, that looks like a line, but if I cover that up, it looks like a cube graph from Unit 2. So that actually occurs twice and counts as 2 turns if you were counting. So if you were to count this up to go back and make sure that it abided by this chart, right? Because if it's a quartic, it would have to have 3 turns in it. And if it's a quintic, it would have to have 4, and a 6th degree would have to have 5. So let's see how I figured out that this was a quartic. If I were to count the number of turns in this graph, okay, it would count 1, 2, 3. And so there are 3 turns making a quartic. And the function that this would be described by this would be f of x is equal to, again, I put that at -3. So if this is at x equals -3, then the factor would be x plus 3. It is linear, so it has a little 1 right here. But this one right here that's at 4, the one at x equals 4 here, would be x, if it's equal to 4, this would be minus, and then we would actually write it down 3 times for a total of 4 factors. But since we would be duplicating it, it just would be easier to write x minus 4 to the 3rd power, and that directly matches the fact that that looks like a cube graph. Again, if we look at that, it looks like a cube graph from Unit 2. So here's another example. This one has a double root right here. It looks like a quadratic right there. And then it also has a triple root. So how in the world did I get that this was a 5th degree polynomial? So if I count the turns, 1, 2, again, a triple root counts as 2 more, 3, 4. You always add, you take the terms and add 1 to get to the degree. And that was the purpose of this chart. Not something you have to memorize, right? But if the number of terms is 4, we would have a 5th degree polynomial. It's just a very good idea to have this in your notes to study. So from here, let's write this function. This function would be f of x is equal to, again, we'll just call this x equals 3. So it'd be x minus 3. Oh, sorry, that's negative 3. So that would be positive. It always changes because you have to set it equal to 0 when you solve it. And it would be squared because it looks like a quadratic. And then we have 3 more of them that are the same at x equals 3. So if this point is x equals 3, then its factor would be x minus 3 3 times. But to save us some time, we put it in there 1 time and put a cube on it. I feel like that's pretty consistent. It's definitely something that once you understand is very easy to understand. Again, if it's 3 here, it's minus 3, and then it will be a cube because it looks like a cube graph. Let's just take a look at that one more time. This, right, looks like a quadratic. It's at negative 3, so it's plus 3. It looks like a quadratic, so it's squared. This looks like a cube graph that we graphed back in unit 2. Transformational graphing of parent functions. That's the parent function for the cube. It's at x equals 3, so it's minus 3 in the factor, and it's cube shaped. It seems like I'm talking a lot about this. I would watch it again. Once you understand it, it's very concrete and it's very obvious on the graph when we look at examples. I really would try to look over the definitions again. I know it seems like a lot to watch, but once you understand the definitions, the problems are actually very easy. So in this particular section of the chapter, the majority of the work is, do you understand the vocabulary in the pictures that I have tried to explain to you using mathematical descriptions? All right, so we're going to look at some examples now. And I know that the notes on this topic are long. They are long. However, the actual work is not very long or difficult. It involves very little algebraic manipulation. It just involves identification of vocabulary topics. So you might need to go back and watch, like if you don't understand why I call something even or odd, you might need to go back and watch that little snippet. Think of the example problems as a way to check your vocabulary knowledge, because once you know the vocabulary, the problems are actually very easy. So looking at these problems, the first thing you need to understand about graphs is that graphs generated by a computer, whether or not you use a program or a website like Desmos, they do not contain arrows. So you'll need to understand that those arrows are there even if they don't show up. If you have a solid or open dot, they will be very evident like this. Okay? So now the first question that's always asked is this graph even or odd? And the answer is this one is, or is it neither? And this one is neither, because in order to have even or oddness, you have to have some kind of symmetry. Keep in mind that even or oddness does not have anything to do with exponents or degrees. It has to do with symmetry of the graph. So this one is neither, and it says why or why not. There is no symmetry. If you have no symmetry, this is impossible. So then B, what is the sign of the lead coefficient? What is the degree? And then name the polynomial. So the lead coefficient is always determined by the right side in behavior. Ignore the left side because the negatives make things opposite, makes it complicated. But the right side, the inputs are positive, so whatever you see the outputs doing, that will tell you what the end behavior is. In this case, it is going down. So the first answer is the coefficient of the lead coefficient will be negative. To determine the degree, you count the number of turns. This is what the chart we were looking at is talking about. So 1, 2, 3, 4. Okay, and this is a triple root. So remember, triple roots count twice. 5 to turn into the triple root, and then 6 to turn out of the triple root. It's important to think of this like a steering wheel. Like if this is a road, you would turn into this root and then out. That steering wheel turn is twice. So this is, it's not a 6. Remember, the chart says that you count and then add 1. So this is a 7th degree polynomial. You could also probably effectively write x to the 7th. I mean, that's the same kind of idea. The name of this polynomial is a septic, but most people would just say, you can say 7th degree polynomial if you want. We typically stop at quintic, because at that point it just gets a little bit I don't know, silly. So you could just call this a 7th degree polynomial. Do not call it 7th degree, right? Because 7th degree what? We're talking about polynomials. You could be talking about a 7th degree black belt or something, right? Which is awesome if you're into the martial arts, but we're talking about math, so make sure you're talking about polynomials. So what are the apparent roots of roots and their multiplicity, and then state their number and nature? So let's talk about what that's talking about. The roots are where the graph crosses the x-axis. So when I look at the x-axis, it's crossing this x-axis 4 times. So there are 4 roots. One of them is at x equals -2. One of them is at x equals -1. One of them is at x equals 0. One of them is at x equals 2. Okay, so that's the first part of the question. What are the roots? The next part of the question is, what is their multiplicity? So this goes into, are you talking about, a double root, or are you talking about a triple root? And so all you do is you just label it. And this one right here, if you just look right here at this thing, let me zoom in on it. That portion of the graph right there is a quadratic shaped graph. So right here you would say double. That's all you have to do. It's going to help us do another part of the assignment. So this is just setting us up for a later part of the assignment. All right. So the next thing is well, what's this? This is only crossing right through. So this is technically a linear root. Same with the next one at 0. It's crossing through one thing. No weird shapes there. It looks like a line. So that's linear. The next one is shaped like a cube graph from the transformations unit. So this is a cube or a triple. That's how you would say it here. You'd say triple root. All right, and to talk about the nature of the roots, we need to talk about how many roots there actually are. And this is really important to talk about how we would list these as an answer. So if we were to list these as an answer, going back to Unit 1 and talking about domain, the domain of this answer is, the domain of the roots is -2, -1, 0, and 2. Even though this is occurring twice, this is occurring 3 times, we would not list them in here more than once. This is the set of answers, but there actually are 7 roots. Okay, and the reason that there are 7 roots is because this one counts twice. So 1, 2, 3, 4, and this one counts 3 times, 5, 6, 7. Now, why is that important? Because of the next question that talks about the nature of the roots. And we've seen that question before, back when we were talking about quadratics. And there's actually a simpler way to do it. What you do is you look at the degree of the polynomial, and you look at how many roots there are. And if they match, then there are no complex roots. No complex. However, if they don't match, then you simply subtract and you can determine how many are complex. A complex root means I cannot see it on the xy plane, as opposed to a real root. So we'd actually probably be better to say this is 7 real roots, are roots that I can see with my eyes on the xy coordinate plane. All right, let's take a look at X and Y intercepts. So this right here is an X-intercept. So we're just going to relabel this using the intercept notation, because I don't want people to forget that though this is a solution or a root, as an X-intercept, it would appear like this, as a point. And that's why when we talked about domain and range back in Unit 1, we also represented some of the answers as points, because you could represent this as a list of points using list notation for the X-intercepts as well. Remember, lists in math use a curly bracket. The Y-intercept, there's only one. There's only ever one Y-intercept, and it is this point right here that crosses the Y-axis. And as I've mentioned before, if something crosses at 0, 0, it is both an X and Y-intercept, always. So then we come down to write a possible equation in factored form. This is pretty easy if you've done part C. F of x would be equal to the factor that produces this x-intercept in this root, which would be x plus 2. And the fact that it is a double root would make it squared. Then we have x plus 1 for the next one. X plus 0 would reduce to just x. So if you ever have 0, you would just use x. And then the last one would be x minus 2. And it would be a triple root, so it would be cubed. So you can clearly see that these factors, if you listed them all out, there would be 2 here, 3 here. This is a 7th degree polynomial. But the fact that it's going down means that I do need to add a negative to the front, and that's why this part right here was important. The fact that I knew that the lead coefficient was negative means that I need to put a negative in the front to make the graph point down on the right side. So determine the domain and range and determine the end behavior. So the domain, we've talked about this since Unit 1. We would start here, beep, the whole time. The domain is negative infinity to infinity. One of the things you'll learn about polynomials is that polynomials, all of the domains and ranges are negative infinity to infinity on every single polynomial we look at. That changes in other chapters, but for now, that is correct for all of the domains. The range is going to change. So this range, remember, we start at the bottom, so beep to the top, and that range will be negative infinity until infinity as well. So they're actually matching. But when I do the end behavior, right, the end behavior is x goes to the left, which is the domain element on the left, so negative infinity. And then the other part of it is the domain on the right, which is infinity, right, because it's going to infinity here. Then you describe the range element that matches that on that side. So when I go to the left side at negative infinity, the range element that's matching it is infinity. It's not in the order of the range, it's which element matches the element in the domain. That's what the end behavior is. And you might not use it. It could be just infinity both times. But in this case, if I look at the right side end behavior, which is here, the graph is pointing down, so I would say that it's going to negative infinity. Approximate the extrema. So the extrema are the mins and maxes. So we need to talk about relative mins and maxes and absolute mins and maxes. So the list for relative mins are the ones that are like downward dips. So here's one right here. Okay, we have a relative min at, one of them is at -2, 0. Yes, it is one of the X-intercepts. We have another relative min here, which will approximate to maybe be -0.5, comma, -1.8. And then we have no others. For my relative maxes, right, for my relative maximum, I only have one relative maximum. Sorry, I have two, just like this. They are the ones that are that are like an upward top of a mountain. So -1.5 and 1.5. Right, it is a point. That's why I said two values, one x, one y. And then here we have one at about 0.8 and 3.8. All right, so now we're going to talk about the absolute minimums and maximums. You have to list these relatives. But if the end behavior says it goes to infinity and negative infinity, that means there is no absolute max, right? Because it goes to infinity. So the absolute max, in effect, does not exist. There's also no absolute min. Okay. So now from this, we can talk about the increasing and decreasing intervals. The graph is clearly decreasing here and here and here, and it does not stop at all decreasing at that moment right there. So to do the decreasing intervals, we'll do decreasing first. There are 3 of them. So it decreases, and just giving the domain of this, negative infinity until -2. That's why it's important to do the mins and maxes first, because the mins and maxes are the places where the increase and decreasing intervals separate. It's also decreasing from -1.5 until -0.5. And these are just, as you can see, they're just x parts of the relative mins and maxes because it is the domain of this interval. And then it also is from 0.8 until infinity. So the increasing intervals, right? The increasing intervals here are going to be where it is tending upwards. So this little tiny one right here, and then also here. So we're increasing from -2 until -1.5. And then also increasing from negative 0.5. And if you ever are reaching for like, what is that? Just go look at what you called it here. Because remember, these domain elements for the relative mins and maxes are going to be directly connected to what happens in these. So then after that, that one will go to 0.8. And keep in mind that this domain and these domains of the decreasing and increasing intervals together are the overall domain of negative infinity to infinity. So one thing I've done is I have decided in the next couple of examples to just type the answers out so that we can kind of just make the other examples go a little more quickly. So you may write these down and then pause and watch me. You can watch me while I'm talking about it and look at the typing and then write it down, whatever best meets your needs here. So the first question is it odd, even, or neither? And it is odd because it is symmetric to the origin. Symmetric at the origin basically means this item is exactly the same here, but it changes the signs from negatives to positives. You can also see it with this point and this minimum, and this right here becomes a maximum. So min to max, max to min, same values, but the negatives and positives are changing, and it is the same shape. It is odd because it's symmetric to the origin. This graph doesn't have an arrow, but you can see that it's tending downward, so it is a negative lead coefficient. There are 1, 2, 3, 4 turns. The rule is count the number of turns and then add 1. So this would be a 5th degree, or x to the 5th, which is called quintic. The next thing that is asked is what are the roots, otherwise known as zeros. You look at the x-axis and you can see that they're at -2, 0, and 2, but we're going to also determine if they're double or not, or triple. This looks like a quadratic, so it is double. This is linear. The assumption is if you don't write anything down, since you wrote it down once, you know that it's linear. You can also write linear there. This is also a double root. And so the question is, well, how many roots are there that are real and complex? So a lot of students get confused because they see 3. But remember in Unit 1, if we were to write this list out, -2, because it's double, occurs twice. Then we have 0, and then we have 2 that's also occurring twice, but because we don't write repetitive ones down, we cross these out of the list, turning 5 answers into 3 answers. So there are 5 real roots, and if this number matches this number, there's no room for complex, so there are 0. The next example will include some complex. So then we write these as x-intercepts by simply taking them and writing them as their point values. Please keep in mind that these items are actually points here. That's -2, 0, that's 0, 0, and that's 2, 0. The y-intercept is also 0, 0, as I've mentioned before. If you have an x-intercept at 0, 0, the y-intercept will also be 0, 0. So then the next thing we're going to do is write down the function, like a possible function for this. So we take the -2, we change it to a +2 in a factor. The 0 will be just x, because x plus 0 reduces to x. The +2 becomes a -2. The double becomes a square. And then the negative lead coefficient we put on the equation right there. All right, to talk about the domain, we just go back and do the beeping thing that we've done in the past. So we would beep from here, beep, right here, beep, to there. About -2.3, you could say 2.4 to 2.3 or 2.4. Make them the same value since we know that it is symmetric because it's odd. I use a solid square bracket because of the solid dot. The range starts at the bottom, so beep to the top. Again, solid brackets, -3 to 3, pretty clear where those are. So the end behavior will change a little bit. Again, on the left side, it doesn't go to -infinity, it goes to -2.3. And on the right side, it doesn't go to infinity, it goes to 2.3. So what does the output go to? It goes to, here it goes to 2, and here it goes to -2. And a lot of students will say, well, why didn't you use -3 and 3? You told me it was the range. No, I said it's elements of the range. So are 2 and -2 within the range of -3 to 3? They are, and at the left side, it goes to -2.2, and the output stops at 2. Keep in mind that -3 and 3 are middle behaviors, not end behavior. It's end, not anything else. Okay, so my relative minimums, I'll show you those with a purple dot. I have a relative minimum here, and here, and here. Now, a lot of students will be like, I understand here because it goes from increasing, it goes from decreasing to increasing, decreasing to increasing. Here, you're decreasing and you stop. So you're decreasing and you change. So that's also one, right? And so the next one is, what are my maximums? My maximums are here and here, but also here for the same reason. Boom, I change to increasing, increasing to decreasing, increasing, decreasing. And to determine the absolutes, you always pick from your list. So which of these relative minimums has the smallest output value? That has the smallest output value, so it's my absolute minimum. Which of these answers has the largest output value? This one. So I pick it as the absolute maximum. All right, it's increasing from here, right? So it's increasing on this interval. It's also increasing on this interval. Notice the values I use for my increasing intervals include the input values of the mins and maxes. They have to, because the min and max is defined as a change from increasing to decreasing. So from -2 to -1, increasing from 1 to 2. These are always open unless there's an endpoint. So here, when I look at the decreasing intervals, we're going down there, square bracket, open bracket, parentheses. Here, they're going down on this interval, and it's also decreasing here. So the first one, -2.3 to -2, 1 to -1 to 1, and 2 to 2.3. The brackets are because of the endpoints on the original graph. All right, let's take a look at another example. So this one, we're finally going to have some complex roots. All right, this one is even. Even means this, okay? It's symmetric to the y-axis. Very easy definition, right? So that's even because it's symmetric to the y-axis. Again, it is negative. Keep in mind, I've mentioned that computers cannot draw arrows, so you have to put them on there. This side is going down, so we have a negatively coefficient. Once again, it is a 6th degree. Let's explore why. Let's count the turns. We're going here, we go in here, we go out there. So you go into the turn, out of the turn. That's 1, 2, 3, 4, 5. And so the rule is you count the number of turns, right? And then you add 1. So we have 5 turns. That would be 6th degree polynomial. Then we look at the zeros, okay? And if we look at the zeros, we can see that we have, the roots or the zeros. We have one at -1.5 and 1.5, and that is 2 real roots. They're not double, they're clearly linear. So this is where we have a complex. If this number and this number do not match, that's when you have complex. And the complex are the ones you cannot see here. So just by some deductive reasoning, if there's supposed to be 6 zeros and I can only see 2, there are 4 hidden from view, making them complex. Another thing to remember is that complex roots have to occur in pairs because they come from taking the square root of a negative. So there's always a plus minus. So this answer can only ever be 2, 4, 6, 8. It can never be 1 or 3. So again, complex roots occur because of these not matching. Notice on the other examples, 5 and 5. Here I had 7 and 7. So the reason I have no complex in those is they match. But here, deductive reasoning tells me if I can only see 2 and they're not doubles to give me more, then it's just a simple subtraction. All right, so to write them as X-intercepts, I write this as -1.5, 0, and this is 1.5, 0. My Y-intercept in this case is here at 0, 3. It's the first example where it wasn't in the origin. Keep in mind, if you have an odd graph, you're going to have an X and Y-intercept of 0, 0 because oddness requires you to go through the origin. So an interesting thing happens. If you have complex roots, you cannot write a possible equation because there's missing information. So if this ever happens, for part E, you would say possible equations cannot be written, or there's missing information, or just does not exist. I wanted to write that sentence out so you could understand why that's impossible with complex roots. The domain of this graph is -infinity to infinity. The range is -infinity stops at 3. I just noticed a little typo. That should be a square bracket. All right, and so to look at the end behavior, as the graph goes to -infinity, right, the graph is pointing down. So at -infinity on the x-axis, we're going downward. So -infinity goes to -infinity. On infinity on the x-axis, it's also going down. So in this case, I used this element of the range twice, and I never used the 3. I want you to think about it. Is the 3, it is part of the range, nice, right? But is it an end value? Is it in behavior? It is middle behavior. So of course it will not show up in this, which is in behavior. Relative minimum, if I'm going to -infinity, I do not have one. My relative maximum is this point right here. These are not minimums or maximums. These weird cube shapes, it just keeps going, and I'll explain more about that when we do increasing and decreasing. So I have a relative maximum at 0, 3, which is the Y-intercept. So that would be my absolute because it's the only one I have, and if it doesn't exist in the relative, it cannot exist in the absolute. So now let's talk about increasing, and this will explain why this is not a min or max. If I start here and I start walking up this graph, I never stop walking up this graph. Even right here, I walk in, I walk out. I didn't change from increasing to decreasing. So my increasing interval is from negative infinity to 0. That's why that is not a minimum or a maximum. Same thing with decreasing. So now I start walking down the mountain. Yeah, I walk into this weird thing and I walk out, but I never stop. I never change from increasing and decreasing. It is decreasing from 0 to positive infinity. All right, so hopefully that typing helped. And the next example we're going to look at will require us to use Desmos. So go ahead and get that ready. So this video is going to go over how to graph when you have to use technology. And I'm going to focus on using Desmos. So please go to Desmos and click on the graphing calculator as opposed to scientific or for function. So it's literally this simple on Desmos. You just type in the function. You can type y equals if you want, or f of x. It's up to you. To put an exponent in, you use the caret, which is shift 6. Make sure that you either click here or use the right arrow key to put minus 4x. Make sure that what you typed is what you see on your paper. And you can see it beautifully displays everything. So in the directions, it basically says use your calculator or Desmos to graph the following, sketch the graph, find the minimum, maximum, x-intercept, y-intercept, everything you need to make a highly accurate graph. Well, on Desmos, all you have to do is hover. Negative 2, 0, 1.155, 3.079, 0, 0, 1.155, comma, negative 3.079, and 2, 0. If you need a better graph, you can either zoom in with this, or you can do it a little bit more precisely with your scroll mouse. Beautiful graph. So why don't we start with that, and then I'll go over what it would be like on a TI or Casio calculator, which on the SAT, obviously you'll need to know how to do that potentially. So what we're going to do to make the graph is we're going to graph it using an axis. There's a lot on here, so I'm going to just go by 1/2. So here I will put a 1, meaning each tick mark is 0.5. So we'll just fill that in. Here we'll do the same thing. And the same thing over here. So then what we do, right, after we do that, is we're just going to graph, and we might need to go back and write down what Desmos showed us. You know, Desmos showed us that we have negative 2, 0, 1.155, 3.079, 0, 0, 1.155, negative 3.079, and 2, 0. And if we want to know what these endpoints are, see how the endpoints are negative 2 to 2, what we would do is we would just hit enter and say, hey, Desmos, what is x equals negative 2? And it tells you, okay, boom. And then I can say, well, hey, Desmos, what is x equals 2? And it tells you it's 2, 0. Notice that the interval is inclusive, so that those will count as x-intercepts or roots. So we just get out our pencil or pen, and we just start graphing the points that we saw. All right, and then negative 1.155, 3.079, just a little bit past negative 1, a little bit above 3 will do. It's just an approximation. And then what we do is we draw a nice curved graph that looks like the shape that we see on our technology. Now, to do this on a Casio or a TI, it is more complicated and is going to take you longer. And the reason we go over Desmos is in Virginia, we can use it on the SOL, Standard of Learning test. So here are the screenshots for a TI calculator. You type in the function into Y1, you then graph it, you hit second calc, you hit graph to graph it, then you hit second calc to find the min or the max. Then you go and hit second calc again, and you use the value feature to find the Y-intercept, and then you hit second calc to find the X-intercept. It is called root on the TI, and you have to do it 3 times. On the Casio, it's very similar. You go to menu, you type it into the function, you then hit the graph menu, and then you follow gsolve to find these same items. All right, so our job was to make that graph and then go over the same questions we did on the front here. So I have copied a picture of the graph here, and we can go over what has happened. So Again, if you need a little bit more help on the calculator, I'm sure there are videos that you can watch on how to do that. So here, what we're going to do is we're going to look at, is it odd, even, or neither? It is symmetric to the origin. You can clearly see these points being the same, but positive and negative, clearly symmetric to the origin, so it is odd. It is going upwards here, so it is positive, and you can see the full graph here, so you know it's going upwards, so it's a positive. It has 1, 2 turns. You add 1 to the turns you see on the graph to learn that it's a third degree, or x to the third problem, called cubic. You then would look at the x-axis to find any roots. Keep in mind, I think I forgot to mention, on a Casio, these are called zeros, just as I've mentioned, and on a TI, they're called roots. They are synonyms. So we can clearly see that we have a root at -2, 0, and 2. They are real because I can see them. And this number right here, right? So this number here matches everything in this statement. So there's nothing hidden from view. There's no complex. If I only saw one root, right? If it only crossed once, let's say I had a cubic that looked like this, right? That's only one root. So how many would be imaginary? Well, if I only have one root that I can see and there's supposed to be 3, then there would be 2. And keep in mind that complex roots always occur in pairs. So to rewrite this as intercepts, we write it as -2, 0, 0, 0, 2, 0. The y-intercept is also 0, 0. You see that happening a lot. It has to happen with an odd function because it has to go through the origin to be odd. The function would be to reverse this and make this x plus 2. 0, 0 would be x plus 0, but that's not appropriate. It is not simplified, so just x. This would be x minus 2. This has no exponents, unlike the 3 examples I did previously, because there's no double roots, right? These are all linear single roots. The domain goes from here, so beep, goes from -2 to 2, solid dots, which come from the fact that it gave me a bracket. Be careful, if one of these was a parentheses, it would go right into here as well. The range starts at the bottom, beep, and it's slightly off because it's not -3 to 3, it's actually -3.079. And that's how I would know that a student was having trouble, that they didn't actually look at technology, because of the fact that they didn't include those decimals, right? Those decimals needed to be included because they came from the technology. And so the domain on the left side stops at -2, and its output value is 0. And on the endpoint here, it goes to 2 and is 0. Yes, the range is -3.079 to 3.079, but those values, they are not at the endpoints. They are in the middle of the graph. So relative minimums, I have one at -2, 0. And if we want to stay consistent, that one should stay first because they do come in order. So give me 1 second to adjust that. So the first one that we encounter is the endpoint, -2, 0. The next one we encounter is this point right here. This is also a minimum, so 1.15, -3.079. My maximums are here, 1.155, 3.079, and 2, 0. The reason that this is a maximum is it goes from increasing to decreasing. This one goes from decreasing to increasing. So let's talk about that. It may help some people understand how this works. So we are increasing here, and we are increasing here, and then we are decreasing here, and that change is what provides the minimums and maximums. Notice here it's nothing and then goes up, so we're changing from nothing to increasing, so that would be a maximum, and this one is increasing and then stopping. So I mean, think about a walk. If you were walking here, this is a low point. You started low, you hiked up a mountain into a valley, and then you came back to a high point. So thinking about it as a hike really helps. So once I do that, what I'm going to do is I am going to take a look at which of these is the largest or smallest. The absolute minimum is the one that has the lowest, smallest output, and that one would be the second one, right? So you can clearly see here that this number is smaller than 0, so that's my absolute minimum. And here, remember, I'm looking at outputs for this. This one is bigger than 0, so that's my absolute maximum. You can already see the increasing interval here, right? So -2 to this point, which is 1.155. We're also increasing from 1.155 to 2. We use a solid bracket there because they are defined points. Please keep in mind that shared points are always parentheses because they're shared. They can't be both increasing and decreasing at the same time. So it's decreasing from -1.155 to 1.155, and that includes parentheses because these values, look, I mean, they're shared. They're here and they're here. So you can't put a bracket on one. How could it be increasing and decreasing at the same time? So if that confuses you, I know some people have trouble with, is it bracket, is it parentheses? Endpoints get brackets with increasing and decreasing. All right, I hope you enjoyed this lesson in this video, and I hope you have a good day today.